Hi everybody, my name is Diego Patino. Today, I will present the paper Learning to Navigate in Turbulent Flows with Aerial Robot Swarms, a cooperative deep reinforcement learning approach. In this work, we developed a method to aid a team of UAVs to navigate in turbulent winds. These winds are characterized by high Reynolds numbers. In the Navier-Stokes equations, our strategy consists of sharing information between UAVs with a graph neural network in order to learn and compensate wind patterns. This problem has been addressed in previous approaches, with two major drawbacks. A. In some methods, the wind fields are known a priori and are often stationary. This creates problems when the method needs to generalize to unseen scenarios. And B. Some methods learn to associate X, Y, Z coordinates to the wind field, again creating generalization problems. In our setup, we set a team of robots to follow a task while operating in a turbulent wind. For simplicity, we command the robots to just stay in formation, but any trajectory tracking task is allowed. Note how the robots fail to stay in formation, with only the PD control acting. To overcome this, we proposed a method to disentangle wind compensation force from the trajectory tracking action. Our method's wind compensation component consists of a reinforcement learning strategy that uses shared information among the robots to compensate for the wind force. The key component of our proposed method is the information sharing between members of the robotic team. To model this information sharing, we use the soft actor-critic strategy to train our reinforcement learning method. Then, we model the actor and the critic as graph neural networks. The graph represents the connectivity between robots in the team and defines which robots can communicate with each other via the adjacency matrix. Thus, the architecture of our reinforcement learning approach takes as input the collection of state vectors at each robot, along with the adjacency matrix. Then, it computes control actions sampled from a policy distribution. In our architecture, the features at each layer depend on the neighbor's features. At time t1, we compute the PD control action to move a robot into a target state. We then let the robot move perturbed by the wind, while simultaneously simulating the robot movement if only the PD control was acting on the robot. At time t2, we compute the difference between the real observed state and the simulated one. We call this difference the state error. In our reinforcement learning method, we define the state space as the concatenation of the state error, the relative position of a robot with its neighbor, and the sensor measurements at each robot. To train our model, we define the reward signal as the negative of the weighted sum of the state error components. Note that minimizing this error leads to maximizing the reward. Our experiments show a significant decrease in the position and velocity errors when our L method is aiding the PD control. The video on the left shows how our method compensates for the wind forces exerted on the robots. This allows them to fulfill their task to stay in formation, regardless of the wind patterns. For comparison, the video on the right shows the PD control acting alone to both keep the formation and compensate for the wind. Note how, in contrast to our method, the PD control alone struggles to keep the formation due to strong wind disturbing the robots. We conducted an ablation study to evaluate whether the performance of our method follows from the information sharing via the graph neural network, or if it is an effect of the network's capacity. To do this, we compared our method with several architectures that only use MLPs at each robot, with no communication allowed between them. Our results suggest better performance when the robots are allowed to communicate to learn the wind patterns using our graph neural network. Additionally, we conducted an experiment to evaluate the capacity of our approach to generalize to larger teams. Our results show that the position error stays low when testing on an increasing robot team size. In summary, we present a collaborative multi-robot method for trajectory tracking in turbulent flows. Our method effectively compensates for the wind force, allowing the robots to navigate smoothly. Our GNN-based approach is scalable because it only uses information from its closest neighbors in the graph. Thank you, and please refer to the paper and the supplementary material for more experiments and results.